This module covers backward erosion piping. Here are the learning objectives for this module. Identify the internal erosion processes, explain situations where backward erosion piping may occur, assess the likelihood of initiation, and assess the likelihood of the hydraulic condition for progression. This presentation will provide an overview of the internal erosion process of backward erosion piping, or BEP, and will describe the geometric and hydraulic conditions for initiation. Although progression of internal erosion is a separate presentation, the unique aspects of the hydraulic condition for progression related to backward erosion piping will be discussed in this presentation. Overview of internal erosion process. Backward erosion piping is an internal erosion potential failure mode for levees and embankment dams that has historically caused numerous failures. It is defined as detachment of soil particles at a free, unfiltered surface in which the process gradually works its way towards the upstream or water side of the embankment or its foundation until a continuous pipe is formed. To occur, there must be a flow path or source of water, an unprotected exit such as a free face or inadequately filtered exit from which material can escape, erodible material within the flow path that can be carried to the exit, and the material being piped or the material directly above it must be able to form and support a roof or pipe. In this series of graphics, the potential failure mode is depicted to first initiate due to heave of a clay blanket, as in Figure A, causing seepage from the sand substratum, as shown in Figure B. Flowing water in the sand substratum can cause migration of sand particles from the substratum, causing it to boil out of the ground, which in turn can result in the formation of a void or pipe below the boil, as shown in Figure C. If a pipe forms and progresses through the sand substratum to the river or reservoir and continues to enlarge from erosion, as shown in Figure D, it can eventually cause collapse of the overlying embankment and breach, as shown in Figures E through G. This figure is an illustration of the physics of backward erosion piping. The process includes 1. Darcian flow, 2. Exit-related hydraulic conditions such as orifice flow, pipe flow, or constant head boundary conditions, 3. Liquefaction or fluidization at the pipe head due to concentrated flow, leading to 4. Occasional bursts of high suspension solids into the pipe, 5. Laminar flow conditions in the open pipe which cause 6. Sediment transport along the bottom of the pipe. All 6 must be occurring simultaneously for piping to progress to failure. In this typical backward erosion piping event tree, Node 1 is related to geologic conditions or material susceptibility. Node 2 is related to the presence of an unfiltered exit. Nodes 3 and 5 address the hydraulic conditions for initiation and progression of backward erosion piping respectively. They will be discussed in more detail on the next slide. These 4 nodes are the focus of this presentation. The other nodes are discussed in separate presentations. Node 4 assesses the mechanical condition for progression, in other words, roofing. Nodes 6 and 7 are unsuccessful intervention and breach, respectively. Use the generic sequence of events or event trees as a starting point for potential failure mode evaluation, but adapt for site-specific conditions. Nodes 1 and 2 are a reordering of the generic event tree to allow pruning sooner if the geologic conditions or material susceptibility do not exist, or a filtered exit exists. For horizontal exits, the probability of initiation equals 1, since it just takes a gradient to detach soil particles at the seepage exit. Teams may also reverse the order of nodes 4 and 5 because the pipe will not be developing unless the hydraulic conditions for progression are present. Two types of hydraulic gradients are evaluated for backward erosion piping. Node 3 assesses the likelihood of heave or blowout, which involves fluidization or liquefaction near the exit. In other words, the classic Terzaghi zero effective stress condition. For this node, there is a critical gradient above which soil particles are detached, and it is assessed using exit or local gradients. The factor of safety represents an upper bound, and initiation occurs at significantly lower values in many cases. For example, data from Turnbull and Mansur for the lower Mississippi River. Node 5 assesses the hydraulic condition for progression of the pipe upstream or riverward. It considers sand transport and pipe formation and is assessed using average or global gradients. Situations where backward erosion may occur. During a risk assessment, multiple failure pathways will be identified and may need to be evaluated. This slide provides examples of multiple locations for backward erosion piping that were considered for Magnolia Levee. Some pathways were screened, some were assessed semi-quantitatively, and some required a quantitative assessment. Finding the weak link in the foundation based on geomorphology, previous levee performance, and other factors is critical. Surface geology is a major factor influencing locations of backward erosion piping, especially in regard to levee alignment. Geomorphology for point bar deposits along the Mississippi River and other major waterways in the United States is particularly difficult to model accurately, where the blanket is heterogeneous and composed of clay-filled swales with sandy ridges between the swales. In the figure on the left, ridge and swale topography in point bar deposits concentrates seepage and results in more observed sand boils. It is important to understand that three-dimensional concentration of seepage, once a defect has formed, will also make progression to breach more likely. In the figure on the right, seepage is particularly concentrated in sandy ridges, where the edges of swales intersect the levee toe in instances where the long dimension of swales is parallel to the levee or intersects it at a small angle. Clay plugs and channel fillings are also depicted and concentrate seepage with a similar effect, but considerably accentuated owing to their greater thickness and width. This slide demonstrates how understanding previous levee performance and river geomorphology help identify likely locations where backward erosion piping may occur. Levee reaches are shown in relation to locations of piping in 1995 and identified swales for Fort Chartres levee district. The majority of the levee reaches with the high and medium likelihood categories occur near intersection of swales with the levee and where the swales run parallel to the levee. The authors believe the strong correlation with previous piping occurred because these pipes have not healed as once thought, but have remained as preferred pathways of higher permeability, needing less gradient to reactivate in future flood events. Here are some more examples of how the river geomorphology is related to expected levee performance. On the left is an example from the American River North levee system, which shows two historic channel deposits mapped perpendicular under the levee. Channel deposits are described in geomorphological maps as being sorted sands and silts fining upward. Although there has not been any documented underseepage performance issues in this reach, these areas were further evaluated for backward erosion piping under the full range of potential flood loading. The Inslee levee system, shown on the right, is located in point bar deposits. The top stratum consists of varying layers of clay silts, and silty sands from 5 to 25 feet thick, underlain by a layer of sand and gravel. Seepage was mainly concentrated on the southern portion of the levee system, where the Mississippi River backs into an old meander of the river. Other contributing factors to this incident include a borrow area and thin blanket located nearby. Geometric condition for initiation, material susceptibility, and continuity. The first node of the typical event tree assesses the likelihood that a continuous path of fine to medium uniform sand exists in the foundation. The geometric condition for initiation requires an examination of the pervious foundation on a particle size scale, in other words, material susceptibility, and field scale, in other words, continuity across the embankment cross-section, and consideration of entrance and exit locations. Silts and clays with a plasticity index, or PI, greater than 7 are not considered susceptible to backward erosion piping unless gradients are very high, which is not likely to occur within a dam or its foundation. It is generally believed that backward erosion piping mostly occurs in fine to medium sand with a coefficient of uniformity, or CU value, less than 3, based on experience and laboratory testing in the United States and Europe. Sources of research data used to generate this gradation plot are listed. Visual examination of the shape of the gradation curves can help to identify soils that are susceptible to backward erosion piping. The range of fine to medium sand is shown by the rectangle. The triangle represents the coefficient of uniformity ranging between 1 and 3. The hypotenuse has a CU of 3, and the long leg has a CU of 1. The slope of gradation curves falling within the triangle would have a CU between 1 and 3. As a caution, do not limit evaluation to just coefficients of uniformity between 1 and 3. Although these soils are generally most susceptible to backward erosion piping, soils with a CU greater than 3 can also be susceptible to backward erosion piping. However, as the CU increases significantly, the soils become more susceptible to internal instability. Reclamation's A.V. Watkins Dam in Utah was a case where the overlying blanket contained thin, hardpan layers that formed the roof for backward erosion piping of underlying fine sands into a downstream ditch. The horizontal gradient was calculated to be 0.06. The dam is 36 feet high at its maximum section and slightly more than 14.5 miles long. The dam nearly failed in the same general area of a seepage incident during initial filling that required installation of a tow drain. Muddy seepage was noticed by a rancher. 140 to 190 gallons per minute was exiting from sand boils. Gradation and hydrometer analysis results for PW07-01 at the downstream toe were shown. Below about 5 feet, the soil samples were classified as SP, SPSM, or SM, with coefficients of uniformity ranging from 0.99 to 2.89. A backward erosion piping failure mode initiated at Wabash Levee Unit 8 in an excavated landside ditch. At the time of failure, the White River was experiencing water levels equivalent to a 7-year flood event. The water level at the time of breach was not at a significant level compared to previous historic and even recent events, and the flood crest is currently listed as the 13th highest. 2 borings were drilled on either side of the breach. The gradations shown are the first 2 samples immediately below the roof-forming material from each boring. Coefficients of uniformity range from 2.0 to 3.6. In addition to site characterization, geomorphology, and levee performance, data preparation for backward erosion piping involves gradation data evaluation, as discussed on the next few slides. Spaghetti plots, like this one from Magnolia Levee, are not useful unless the data is parsed by depth, with samples lying just below the roof-forming material of most interest. However, even that parsed data may be misleading if none of the samples are from the critical locations or weak link in the foundation. This mass gradation plot was subsequently pared down to the depths of interest and below the roof-forming material. The equivalent opening size, or EOS, shown on this plot is the range of openings in a filter fabric placed beneath riprap at a downstream seepage exit. This example from Whittier Narrows Dam shows the results of post-processing of gradation curves to concisely show median and quartile ranges for the foundation gradations for 3 depth ranges. The data shows how the foundation soils become more uniform near the surface. It is also essential to properly classify the soils according to the Unified Soil Classification System, or USCS, using ASTM standard D2488. This requires a critical review of historic data and possible reclassification as part of the site characterization. These figures from Magnolia Levee show how USCS group symbols, fines content, gravel content, and coefficient of uniformity were binned, as well as a scatter plot showing the distribution of coefficient of uniformity based on ground surface elevation. This type of data presentation can be helpful in assessing the susceptibility to backward erosion piping. However, do not place too much emphasis on statistical evaluation without meshing the results with site characterization, geomorphology, and performance data. As previously discussed, discrete layers or channels can govern backward erosion piping, which may be missed in a boring and statistical evaluation. In this plan view from Mohawk Dam, the green lines are potential seepage paths around a partially penetrating sheet pile seepage barrier, shown as a red line. The alluvium thickness and elevations of low coefficient of uniformity soils are shown at discrete boring locations. Although these are point estimates, elevation contours or heat maps could then be generated to help inform the backward erosion piping evaluation. It is paramount to having good site characterization drawings to scale to understand the piping path and continuity of material susceptible to backward erosion piping beneath a roof-forming material. This example is from Bolivar Dam. In this example from Proctor Dam, selected gradations are included with the boring data and embankment cross-section to illustrate the presence of continuous materials susceptible to backward erosion piping beneath a roof-forming material. Pictures of the soil samples, along with the gradation curves, like these from Bolivar Dam, are also helpful to understand the susceptibility to backward erosion piping. Open cut exposures can be an invaluable resource to understanding foundation conditions not revealed by widely spaced small diameter borings. During the risk assessment for Mohawk Dam, Wahonding Quarry was visited. It is located 3 miles upstream of the dam and provides continuous lateral exposures of the stratigraphy of the foundation and terrace outwash deposits beneath the dam. The top left is a Google Earth image of the Wahonding Quarry showing the locations of the excavated exposures of Wisconsin and outwash shown in other photos. The photos at the top right and bottom left are the west-facing wall showing cross-bedded sands truncated by planar bedded sandy gravels with well-rounded gravels. The photo at the bottom middle is of the north-facing wall showing sequences of cross-bedded sands with gravel bounded by erosional surfaces. The flow direction indicated by the red arrow is approximately parallel with flow to the right. Lastly, the photo at the bottom right is of the northwest facing wall showing sequences of cross-bedded sands with gravel bounded by erosional surfaces. Flow direction is approximately perpendicular with flow coming out of the page. Geometric condition for initiation. Boundary conditions at the seepage entrance and exit. Assessing the seepage path length requires an understanding of the upstream or water side and downstream or land side boundary conditions. The next set of slides will examine potential seepage entrance and exit locations. In this plan view of Mohawk Dam, the team identified various defects in the alluvial top stratum, which were considered as potential upstream seepage entrance locations. These were used to evaluate various seepage paths. Vegetation in the floodway can be naturally occurring or planted in riverside borrow areas. This vegetation can constrict and concentrate flow along the levee alignment, leading to riverside scour of the top stratum and levee embankment, directly connecting the foundation sand to the river and shortening the seepage pathway. The vulnerability of the levee to scour erosion is further exacerbated when the levee alignment protrudes into the floodway or is located on an inside bend. At Missouri River Levee Unit L575, timber and thick vegetation in old borrow areas in the floodway contributed to focusing flows between the levee and the wooded area, which led to erosion of riverside clay blanket along the toe, and ultimately the levee breached. The aerial photograph on the left shows the vegetation in the floodway and a potential flow constriction adjacent to the levee alignment. Hydraulic modeling illustrates the concentration of flow for this alignment, with the highest velocities shaded red where the levee protrudes into the floodway. This slide presents cross-sections of the L575 levee, showing how scour can affect the seepage path length. In the top figure, the seepage path length is from the river channel to the landside toe of the levee, or possibly from an intermediate chute if it penetrates the top stratum. In the bottom figure, scour has occurred in the chute, and a scour hole has developed adjacent to the levee due to the flow concentration shown on the previous slide. The scour hole has reduced the seepage path length significantly since the entrance has moved from the river channel or chute to the scour hole at the riverside levee toe. The exit is the landside levee toe. Therefore, scour erosion can be an initiator for backward erosion piping. In this example from Bolivar Dam, potential exits through defects in the alluvium downstream of a filter blanket were reviewed. For the same exit location, two different seepage paths were evaluated because of the dam alignment. Node 2 of the typical event tree assesses the likelihood that an unfiltered exit exists. Three types of exit conditions are shown on this slide. A planar exit is shown in the top figure, where an open exit is present naturally, for example, when no top stratum is present at the land side. A top stratum is present in the middle figure, but a ditch penetrates a substantial portion of it, leaving a relatively thin cover layer over the foundation sand. In other cases, the exit point is created when the cover layer cracks or hydraulic fractures locally, as shown in the bottom figure. The top and middle figures generally represent a two-dimensional seepage scenario, whereas the bottom figure results in a three-dimensional scenario with more converged flow towards the pipe head and towards the pipe in plan, as well as from depth. These holes can result from uplift-induced cracks or natural or man-made penetrations through the cover layer. The potential for heave or blowout in the field is greatly influenced by geologic details, details of man-made features, climatic conditions, as well as biological and chemical processes such as excavation by rodents, plugging of seepage exits by biofouling, or mineral deposition. These defects or weaknesses can lead directly to an unfiltered exit or increase the likelihood of heave or blowout. Geotechnical site investigations will not always discover defects or weaknesses that govern performance. At Mohawk Dam, potential exit locations were reviewed that included areas of thin to no alluvium top stratum. The plan view on the right shows the results of a hand auger investigation, which found the alluvium was only 2 to 3 feet thick. At the left, an unfiltered exit is provided by an overturned tree with a root ball that penetrated the alluvium. For scale, the person standing next to the stump is over 6 feet tall. This photograph highlights the importance of stump removal as part of tree removal. The decayed stump can result in a deep vertical void that penetrates the top stratum and provides an unfiltered exit. In this figure, backward erosion piping channel formation is shown with initiation at 2 potential locations near the embankment toe for illustrative purposes. Both would not form simultaneously. Upward vertical hydraulic gradients are resisted by gravity and relate to the potential for heave or blowout and the possible initiation of backward erosion piping. Horizontal, or nearly so, hydraulic gradients are internal gradients along a seepage pathway. However, gravity is not a resisting force, and little to no horizontal gradient is required for initiation of backward erosion piping, as reflected by the note on the typical event tree to assume a probability of initiation of 1 for horizontal exits. The gradations from Wabash Levee Unit 8 were discussed previously. A farmer dug a ditch at the landside levee toe to help drain a farm field, creating a horizontal seepage exit. The levee ultimately breached. Sand boils will be discussed in the following section. What is a sand boil? Some common definitions are shown on this slide. Which one do you think is correct? Sand boils are not concentrated seepage, and they're not concentrated seepage with surface material rearrangement. Sand boils are erosion of subsurface sands due to the pressure or seepage flow being great enough to cause liquefaction or the zero effective stress condition. Let's compare boils versus backward erosion piping. Boils, where there is a confining layer, result from high gradients across the confining layer. In other words, water pressure in the sand exceeds the confining stress. Boils in unconfined sand result from seepage forces exceeding the confining stress. Many severe boils have occurred without any evidence of backward erosion piping due to very low average gradients in the foundation, but very high gradients across the confining layer. To help understand sand boils versus backward erosion piping, this slide shows 3 potential conditions distinguished by the source of the material deposited. At the left, seepage water is not transporting material as it passes through the surface deposits. The force of the upward flow of water, like a relief well, simply piles up finer grained superficial deposits. For this scenario, there is likely no problem. In the middle, no material is being carried by seepage water when it reaches the surface deposits, but the upward flow is sufficient to remove finer materials from the superficial deposits. This is indicative of a possible problem. At the right, seepage is carrying material from the flow path, which is able to escape, implying average gradients are high. The threat of tapping into the impounded water is great, which is indicative of a potential big problem. The previous slide illustrated not all sand boils are bad. Sand boil observations should be differentiated by size. The size of the sand boil should be measured both by the diameter of the sand boil throat and by the amount of material that is being deposited on the surface. These are direct indicators of backward erosion piping. Therefore, guidance to standardize sand boil descriptions has been included in Draft Engineer Manual 1110-2-1913. The throat diameter can be compared to how much of the hand can be inserted from one finger to more than a fist. The terms pin boil and descriptors like small, medium, and large refer to the throat diameter. The size of the sand cone formed by the sand boil measured as the diameter of the sand boil footprint, is also an important characteristic and relates to how active the sand boil is transporting foundation material. The activity descriptor should indicate how much material is moving from the boil. The terms low activity, moderate activity, high activity, and very high activity should be added to the size descriptor to indicate the amount of material moved and can be compared to the relatable objects of wheelbarrows and refrigerators. For example, a sand boil with a throat size of 3 inches with more than 6 cubic feet of accumulated sand would be described as a medium high activity sand boil. Although intended for classification during flood fighting, this guidance can be utilized during a critical review of previous levee performance. For Mohawk Dam, all previous sand boil observations were reclassified using this guidance to help calibrate the team and overcome previous biases. The magnitude of underseepage observed during a flood event is usually a good indicator of initiation of backward erosion piping. Generally, the underseepage conditions worsen as the river elevation rises and often respond relatively quickly to changes in river elevation. Underseepage is generally estimated based on an estimated quantity of seepage water emerging from the ground from the landside toe and landward of the levee. The following definitions of underseepage are recommended for use in flood events so that consistent comparisons can be made between flood events and levee systems. This guidance can also be used to help calibrate the team and overcome previous biases. The descriptors on the previous slides for underseepage and sand boil size are illustrated in these photos. On the left are examples of underseepage magnitude, and on the right are examples of various sand boil size and activity. Hydraulic condition for initiation. Node 3 of the typical event tree assesses the likelihood that sufficient exit gradient exists to initiate backward erosion piping at an unfiltered exit. For backward erosion piping, there is a critical gradient above which a particle is detached. In other words, local or exit gradient considerations. First, some terms need to be defined. For vertical exit conditions, heave is a condition when the saturated sand specimen, subject to upward seepage, suddenly decreases in density and increases in permeability. The vertical hydraulic gradient at this condition is referred to as a critical gradient and describes the gradient resulting in zero effective stress, more commonly envisioned as quick conditions. If the uplift pressure exceeds the weight of the confining layer, uplift can initiate and result in significant changes in the seepage regime. Uplift can form a new seepage exit beneath the confining layer, where hidden deterioration can occur from concentrated seepage if horizontal gradients are high enough. Blowout ruptures the confining layer, providing an unfiltered exit to the ground surface. The location of the rupture may be the result of a defect and/or the location of maximum uplift pressure. If hidden deterioration was occurring before the blanket is ruptured, these locations may be coincident. When assessing, consider assumptions for seepage conditions, tailwater conditions, degree of saturation, and density of confining layer. Uplift can also initiate in partially saturated confining layers, especially for lightweight soils such as peat or soils with high organic content, or cohesive soils in cases of drought. The likelihood of heave can be evaluated using the first order, second moment method of reliability analysis. This approach is commonly used to perform a probabilistic seepage analysis using vertical exit gradients obtained from software such as SeepW. This method assumes that the blanket is intact and initiation of backward erosion piping occurs from uplift and cracking. This slide illustrates how the analysis is performed for a given headwater level. The mean and standard deviation are estimated for the selected random variables. In this example, there are 5 random variables: thickness, permeability, and saturated unit weight of the upper foundation soils, and thickness and permeability of the lower foundation soils. The first run case is for the calculated factor of safety against heave or blowout for the mean values of the random variables. For subsequent run cases, the mean plus or minus 1 standard deviation is evaluated for each random variable while holding the other random variables constant at their mean values. This results in 9 analysis runs for a given headwater level. If 7 headwater levels are evaluated to define the full range of loading, the total number of analysis runs for a given cross-section is 9 times 7, or 63. Thus, the first-order second-moment method of reliability analysis can be very labor-intensive. The vertical effective stress factor of safety should be used in the assessment of underseepage. The vertical effective stress factor of safety is defined as the vertical effective stress that can be developed in the soil divided by the excess pore pressure causing seepage through the soil. This equation is commonly rewritten as the critical vertical seepage exit gradient divided by the vertical seepage exit gradient. The critical vertical seepage exit gradient is the familiar buoyant unit weight of soil divided by the unit weight of water. The vertical seepage exit gradient is a measurement of the head loss over a prescribed distance at the ground surface where water is vertically exiting the soil. Blanket theory has its origins in the method of fragments and other well-established groundwater hydrology solutions that were developed in the early part of the 20th century to facilitate solution of the Laplace equation. On the basis of this solid theoretical background, blanket theory has been used by the Corps of Engineers for more than 65 years as a practical means to calculate flows, hydraulic gradients, and pore pressures beneath levees. Results from blanket theory have been successfully incorporated into the design and evaluation of many levees along the Mississippi River and tributaries and other locations. The basic geometry of a levee under seepage analysis with a top stratum or blanket is shown. Unlike the results from SEEP-W analysis, which required first-order second-moment method of reliability analysis to assess the probability of a factor of safety less than 1, blanket theory has a set of predictive equations for excess head, and hence exit gradient, that can be used directly in a probabilistic analysis to estimate the probability of a factor of safety less than 1 with the right foundation conditions and boundary conditions. The blanket theory cases are summarized on this slide. Riverside boundary conditions can include no riverside borrow pits or seepage blocks, a seepage block, which is an impervious boundary, or a riverside borrow pit, which provides an open seepage entrance, depending on the case. Landside boundary conditions can include a blanket extended infinitely landward, a seepage block or impervious boundary, or an open seepage exit, again depending on the case. Cases 6 and 7 are generally used in the Mississippi Valley Division and are outlined in red. Case 8, which is not shown, is the same as case 7, but has a partially penetrating cutoff wall beneath the levee centerline. The assumptions used in blanket theory solutions are vital to understanding the applicability of the method. Seepage flow is assumed to be laminar, allowing Darcy's law to be applied. The levee is assumed to be an impervious boundary. The flow in the blanket is assumed to be vertical, and the flow in the pervious stratum is assumed to be horizontal to provide an analytical solution. There are also constraints to ensure these flow conditions. The width of the impermeable boundary is greater than or equal to the depth of the pervious stratum, and the hydraulic conductivity of the pervious stratum is at least 10 times higher than that of the blanket. These assumptions are met, the flow net for blanket theory appears as shown. ERDIC Technical Report 18-24 by Brandon et al. 2018 corrects several errors in Engineer Manual 1110-2-1913 published in 2000. Performance observations at instrumented levee sites on the lower Mississippi River as related to vertical exit gradients across the landside top stratum, calculated from piezometer readings, were used to set the vertical seepage exit gradient criterion of 0.5 as empirical means of designing against backward erosion piping. Design methods in Technical Manual 3-424 are based on evaluating the vertical seepage exit gradient through the top stratum at the landside levee toe. The effective stress factor of safety is calculated based on vertical seepage exit conditions. Calculations of exit gradient and factor of safety were then compared to field performance observations as illustrated, leading to performance-based factors of safety, for example, factor of safety greater than 1.6 at the landside levee toe. This slide suggests that most sand boils on the lower Mississippi River occur due to defects in the top stratum, which is why the gradients are lower than the theoretical value for uplift. Sloping exit conditions. It would be unusual to assess backward erosion piping in the embankment exiting on a slope. Through seepage is more likely to lead to slope instability or sloughing. For a horizontal exit or seepage exiting a sloping face, the probability of initiation is probably very near 1. Several researchers have attempted to quantify the critical gradient for sloping exit conditions. All of the methods have the same issue with length scale over which the critical gradient was exceeded, which is very small, for example, less than a 10 grain diameter. Research by Van Beek and others in 2014 suggests that the gradient should be computed over distances of 20 grain diameters. Meanwhile, engineers continue to adhere to traditional approaches of computing exit gradients over much larger distances, such as 0.3 to 1 meter. The length over which the gradient must be examined is too small to be of practical use in field applications, and should not be relied upon as a predictive tool for initiation of backward erosion piping. Therefore, all of the methods listed on this slide are considered unreliable and are not recommended for use. To assess performance of seepage control features, like toe drains, a node can be added to the typical event tree to assess the likelihood of poor performance, which impacts the likelihood of initiation in the subsequent node. This example from Whittier Narrows Dam evaluated the impact of a non-woven geotextile wrapping a previous toe drain addition on the exit gradient and considered various degrees of clogging. Toolbox overview. The RMC Backward Erosion Piping Initiation Toolbox contains two methodologies. First, cases 1 through 8 of the blanket theory, and the second is the first order, second moment method of reliability analysis. References. Here are the primary references for the backward erosion piping initiation portion of this module. Hydraulic condition for progression. Node 5 of the typical event tree assesses the likelihood that sufficient flow exists to advance the pipe to the impounded water. For backward erosion piping, there is a critical flow velocity above which the soil particles will be transported in the pipe. In other words, average or global gradient considerations. The hydraulic condition for backward erosion piping progression includes liquefaction or fluidization at the pipe head due to concentrated flow, leading to occasional bursts of high suspension solids into the pipe, and laminar flow conditions in an open pipe, which cause sediment transport along the bottom of the pipe. In general, there must be sufficient flow to continuously transport detached soil particles to an exit and to advance the pipe to the river or reservoir. It should be noted that progression of the pipe can stop if the average gradient is lower than the critical gradient. This can occur due to the short duration for a critical hydraulic head difference, or by a reduction of the hydraulic head difference by raising the tailwater through an intervention action, such as constructing sandbag rings around a seepage exit. However, subsequent, possibly even lesser flood events may have a shorter seepage path due to previous piping and thus require a lower hydraulic head difference to initiate and progress to breach. The hydraulic condition for progression is evaluated by comparing the average gradient to a critical horizontal gradient. The average gradient is calculated as the hydraulic head difference divided by the seepage path length. In this example from Wabash Levee Unit 8, the hydraulic head difference is 9.5 feet and the seepage path length is 163 feet, resulting in an average gradient in the foundation of 0.06. There are several methodologies for assessing the critical horizontal hydraulic gradient. Creep ratios are an empirical method based on observations of seepage performed for a range of soil types and are among the oldest methods. The inverse of the creep ratio is the average gradient if there are no vertical structures. More recently, methods based on horizontal gradient have gained more attention for evaluating potential for backward erosion piping of cohesionless soils, specifically based on the research of Hans Sellmeier and John Schmertman. Their research involved laboratory sand flumes to study the hydraulic gradient across a structure required to achieve a complete breach. The primary difference between the test is in the Delft test, pipes were formed at a downstream discharge provided in the model, and in the University of Florida test, initiation was forced with a short starter pipe. In addition, the test geometries were not the same. Hydraulic condition for progression, creep ratio methods. Wise creep ratio and Lane's weighted creep ratio are empirical methods based on observations of seepage performance for a range of soil types. An evaluation of creep ratio is informative when the levee consists of fine-grained material and no landside blanket exists. The inverse of the creep ratio is the average gradient if there are no vertical structures. The method is not appropriate for a compromised confining layer overlying a confined aquifer. Duncan and others in 2011 state that while informative, the creep ratio is considered a quick and dirty check rather than a rational method of analysis. The state of practice is to use rational methods based on blanket theory, flow nets, or finite element modeling analysis. And the greatest remaining value of creep ratios lies in indicating the relative erosion potential of various soil types. This figure shows critical sand boil locations observed in 1937, 1947, and 1950 for levees along the Mississippi River. Numerous sand boils were observed at creep ratios greater than 18, or average gradients less than 0.05. Horizontal gradients as low as 0.02 were estimated. Failure nearly occurred at the trotter's location. A typical critical vertical or upward exit gradient in cohesionless soils is often thought to be around 1.0 for a specific gravity of 2.7 where heave is concerned, and higher for cohesive soils not subject to uplift. However, the magnitude of the horizontal gradient that has led to backward erosion piping is much lower. Hydraulic condition for progression, adjusted Dutch calculation rule. Sellmeier and others between 1988 and 1993 developed a mathematical model for backward erosion piping progression for the geometry and boundary conditions shown. Curve fitting of numerical solutions in the process yielded a simplified piping rule used in the Netherlands. The Sellmeier model provided a relationship between pipe length and hydraulic head at which sand grains are in equilibrium. For any head less than the critical head, the development of the channels stops. If the head is increased, erosion begins again. The critical head occurs when the length of the channel, lowercase l, is about 0.3 to 0.5 of the flow path length, capital L. For head less than the critical head, progression of the pipe reaches a stable condition. For heads exceeding the critical head, the piping channel extends upstream and breaks through to the impounded water. The photos show the observed channel formation in Boscarp sand. The flow direction is to the top of the photo. This video is looking down on the top of the flume used in the Dutch laboratory experiments. A planar exit is provided on the right side of the flume, and flow is from left to right. Small channels start to form from the downstream end on the right and progress towards the impounded water source on the left. When the channels reach the water source, the pipe enlarges rapidly. Sellmeier's model was implemented in a two-dimensional numerical groundwater model to account for different configurations and used to derive a calculation rule for a standard levee located on top of a homogeneous confined aquifer. The original and adjusted calculation rules are described in Sellmeier and others 2011. The adjusted calculation rule extended and updated the piping model based on results from a wide range of tests, several small-scale, 7 medium-scale, and 4 large-scale Eichdyke experiments. Thus, the Sellmeier model is known to result in good predictions for large-scale experiments with two-dimensional configurations. The equation for the critical gradient for backward erosion piping progression is comprised of 3 terms: a resistance factor, which accounts for the strength of the layer subject to backward erosion piping, a scale factor, which relates pore size and seepage size, and a geometrical shape factor. Each of these terms will be discussed on the following slides. The methodology is only applicable within the limits of the piping model testing parameters shown. Mean values are used to normalize project-specific values. The resistance factor is a function of White's constant, bedding angle, relative density, roundness of the particles, and coefficient of uniformity, which was established as an important parameter earlier in this presentation. Van Beek and others in 2010 indicate that the KAS and U terms appear to be of less importance than other sand characteristics, and the results of multivariate regression analysis show that they have a weak influence on critical gradient. Therefore, the U and KAS terms and equation for the resistance factor are sometimes ignored in practice. The bedding angle and White's constant have been set to 37 degrees and 0.25 respectively due to model calibration and are not changed in Dutch practice. Since the values were fixed in the multivariate regression, any influence they had is accounted for in related variables. It's therefore not appropriate to vary these parameters. The scale factor is a function of the particle size, for which 70% is finer by weight, the horizontal seepage path length, and the intrinsic permeability of the piping layer. The geometrical shape factor is a function of the ratio of the depth of the piping layer to the horizontal seepage path length. The intrinsic permeability used in the scale factor is defined on this slide. Van Beek and others in 2013 conducted piping experiments on multi-layer sand samples to validate Sellmeier's model, and the piping rule was extended for multi-layer aquifers. A layer-weighted average of permeability is used as shown. When the contrast of permeability is large, and the aquifer thickness is relatively large compared to the seepage path length, the assumption of predominant horizontal flow is no longer valid. Hence the extension of Sellmeier's piping rule from multi-layer foundations can be applied to elongated aquifers with D over L ratios less than 0.3 that have low contrasts of permeability. That is, the ratio of horizontal permeability for the coarse layer to the fine layer less than 10. Hydraulic condition for progression, adjusted Schmertmann method. This slide shows plan and elevation drawings of the horizontal seepage flume used by Schmertmann to investigate piping behavior at the University of Florida. The seepage path length in the flume is 5 feet, and the depth of the sand being tested was 1 foot. This table summarizes the reference test values. In addition to the previously mentioned geometry of the test flume, the reference soil properties of the sand included the particle size with 10% passing by weight, anisotropy, or ratio of horizontal permeability to vertical permeability, and relative density. Schmertmann proposed an average gradient that gives the average factor of safety against piping of the flow path in a soil subject to backward erosion piping without requiring construction of a flow net. The methodology is based around the results of flume test. It incorporated the results from the University of Florida and Dutch testing by applying these correction factors to account for the difference in test geometries. Assessing the potential for backward erosion piping progression requires comparing the horizontal hydraulic gradients in the foundation to critical values as determined from the laboratory. Unfortunately, the laboratory reference values must be adjusted for many factors to be applicable to field conditions. This chart shows the laboratory horizontal critical gradients from Schmertmann 2000. For a very fine uniform sand, the critical horizontal gradient of 1/18 is the same as Bly. This chart is frequently misused in practice when screening backward erosion piping and compared directly to the average gradient in the field without any corrections. The numerous correction factors from the reference test values are listed to obtain the field critical gradient. Similar to the Selmayr method, there is a geometrical factor that is a function of the ratio of the depth of the piping layer to the horizontal seepage path length. The length factor, anisotropic permeability factor, grain size factor, and density factor are defined on this slide. The length factor requires transforming the seepage path length based on the soil's anisotropy. Schmertmann 2000 also had a gradient factor for the dam alignment, which is not often used in practice. Similar to the Selmayr method, Schmertmann's method also accounts for a multi-layer foundation, where the piping layer is underlain by a higher permeability layer. The critical hydraulic gradient decreases when the piping layer has a higher permeability underlayer due to the increased flow into the piping layer. It is obtained by a graphical solution. Unlike the Selmayr method, the Schmertmann method can also assess inclined pipe paths. The field critical gradient adjusted for pipe path inclination is obtained by graphical solution as a function of angle of pipe path inclination for various values of field horizontal critical gradient. The adjustment for pipe path inclination is then back calculated as shown. In practice, laboratory flume tests are rarely conducted to measure the critical horizontal gradient, and the linear relationship proposed by Schmertmann is the primary means for estimating critical gradient values for risk assessments as a function of particle size distribution, specifically coefficient of uniformity. While this figure is quite useful, it is difficult to estimate the uncertainty in the critical point gradient because study averages were presented. For example, one of the single data points is the average from 14 individual laboratory tests. To quantify uncertainty, Robbins and Sharp in 2016 compiled and analyzed over 100 laboratory piping tests to assess the variability of the laboratory measurements of horizontal critical gradient. The results indicated a large amount of uncertainty surrounding the critical gradient measurements for all soils, with increasing uncertainty as soils become less uniform. Critical point gradients from individual laboratory tests were plotted along with best fit quantile regression lines. The best fit median line for all test results indicates equation 19 from Schmertman 2000 is conservative for coefficients of uniformity less than 3 and unconservative for coefficients of uniformity greater than 3. Hydraulic condition for progression. Other considerations. This table summarizes influence factors related to initiation of backward erosion piping, with one significant addition at the end. All other parameters remaining the same, the likelihood of backward erosion piping is decreased by increasing fines content, decreased by increasing coefficient of uniformity, decreased by increasing particle size, decreased by increasing relative density, decreased by decreasing permeability, decreased by angularity of the particles, and increased by increasing thickness of the piping layer, increased by presence of an underlying layer of higher permeability, increased by increasing horizontal to vertical permeability ratio, increased by increasing potential defects in the confining layer, and lastly, probably not significantly affected by confining stress in the erodible layer. Backward erosion piping is highly influenced by scale, primarily aquifer depth. This is one of the reasons why results of laboratory experiments are not directly applicable to practice. Scale effects are considered in the Schmertman and Selmayr models. Scale effects can best be explained by considering the flow towards an exit or pipe head. When an aquifer from which flow originates is larger, the area of flow increases, and more water will be conveyed towards the pipe head or exit. As a result, the flow velocity and gradients near the pipe head or exit increase with scale, and the critical gradient decreases with scale. The influence of fines on the critical gradient for progression of backward erosion piping is significant and has major implications on risk assessments. ERDIC testing of clean, uniform sands and mixtures with non-plastic fines is shown on the left. At a fines content of 5%, the laboratory local critical horizontal gradient for backward erosion piping progression is doubled, and at a fines content of 10%, it is quadrupled. Deltaris testing of tidal deposits in the Netherlands, which tend to be dirtier sands, is shown on the right. The y-axis is normalized critical head. The fracture finer than 0.016 millimeters was used because it provided a better trend. The reason the scatter is higher for the Deltaris experiments is that overall gradients were derived, whereas ERDIC used local gradients which are not as sensitive to heterogeneity. Despite the difference in characterizing the fines, the observed trends are consistent. DeWitt performed experiments with different types of exits while retaining other characteristics such as sand type, seepage length, and thickness. An increase in critical gradient for backward erosion piping progression obtained in these experiments can be observed with increasing exit flow area. For pipe development, a circular exit causes a more converged flow towards the pipe head and towards the pipe, resulting in higher gradients at the pipe head and more erosion in the pipe. The resulting critical gradient reduces with decreasing exit area until the exit begins constraining flow. For a singular defect, the concentration effect diminishes rapidly due to two-dimensional radial flow limitations. There may be pipes forming close to the defect, but the gradient drops rapidly with distance away from the defect and may stop the pipe formation process. In addition, a 3D configuration was found to result in significantly lower critical gradients than those predicted by an accepted calculation model calibrated on the basis of 2D experiments, a finding that is essential for the application of the model in the field. The 2D Selmayr model overestimates the critical horizontal gradient for these experiments by approximately a factor of 2. Thus, when using a 2D model for flow towards a single point, for example, a single hole in a confining layer, the critical horizontal gradient for progression of BEP must be adjusted. Although not developed and calibrated for the adjusted Schmertmann method, a similar reduction for a 3D exit condition is considered appropriate. When a vertical structure, such as a partially penetrating seepage barrier wall, is present in the path of the pipe, the sand downstream of the structure must fluidize before the pipe can pass. The presence of such a vertical seepage path causes large resistance for pipe development. The overall gradient required to pass a structure is usually higher than gradients required for initiation and progression of a pipe without the structure. This chart can be used to assess the effect of a partially penetrating seepage barrier wall on the critical gradient for progression of backward erosion piping. Based on 45 laboratory tests from 6 data sets, Pohl et al. 2019 proposed two equations for the average BEP progression rate. The rate is a function of average hydraulic gradient, soil properties of hydraulic conductivity and porosity, and empirical coefficients. On the left is a multivariate fit, and on the right is an equation based on KESD 1979 that is based on the assumption of proportionality between progression rate and pore velocities at the pile tip. An average rate of 0.1 millimeters per second, or 8 meters per day, was found in the large-scale test, which is the solid red dot in the figures, and is in good agreement with both empirical formulas which yield 0.19 and 0.14 millimeters per second respectively. These rates are relatively close to the 0.05 to 0.06 millimeters per second obtained in the Eichdyke large-scale test on fine sand. The relatively slow progression observed in this experiment indicates the importance of the temporal aspects. If similar rates occur in the field, it takes approximately 1 week for a pipe to develop through a 50-meter seepage path length for a levee. Because uncertainty could be an order of magnitude, a range of rates should be evaluated. Toolbox overview. The RMC Backward Erosion Piping Progression Toolbox contains 3 methods to help assess the likelihood of backward erosion piping progression. The adjusted Schmertmann method incorporates the work by Robbins and Sharp from 2016 to transform into a probabilistic method. The Dutch calculation rule has evolved over time. The most recent is the fine-tuning from Selmayr and others in 2011. Van Beek and others modified the method for multi-layer foundations and reduction in gradient for three-dimensional configurations with flow towards a single point, for example, a hole in a confining layer. Creep ratio methods include Bly from 1910 and Lane from 1935. References. Here are the primary references for the line of creep methods. This slide contains the primary references for the Schmertmann and Selmayr methodologies. Additional references can be found in the technical manual and in the toolbox.